All right. So now what we plan on doing is, kind of understand how the M class CPU actually boots up. So we were on, the programmer's model page, which was page number 10, if I'm not wrong. Yeah, page number 10. What we'll do is scroll down and talk a little bit about um, the vector table, right? So let me just briefly talk about the vector table. So what is a vector table? And why all of a sudden that comes into the picture. So we talked about the CPU having, interrupt lines. So the question is, our original analogy was you're reading a book, which is like the normal execution that the CPU is performing, equivalent to the CPU performing normal work. And then somebody knocks at the door, which is equivalent to an interrupt. So what you would typically do is put a bookmark in the book, go attend to the door, and let's say you don't know how to attend to the door. So what you'll do is you will look for instructions. And let's say the instructions happen to be in another manual, right? Another memory location, so to speak. And you're supposed to read those, attend to the door, and then come back. So in case of an M-class CPU, the question is when an interrupt happens, how does the CPU know where to go to, and find, the code? And the answer to that is something called the vector table. The interrupts in the M-class CPU, we say, are vectored. And what that means is we have this table that, in usual cases, starts from the memory address 0. And then at every 4 byte, we have a number stored, and that number is representing the address of the memory location where the CPU should jump, right? So at every 4 byte boundary, we have a number. That number is representing where the CPU should jump. But then why have so many numbers? And the answer to that is you might have, different interrupts here, right? And depending on which interrupt occurred, which interrupt number was fired, it will pick, uh, you know, the number that is stored on the offset corresponding to that interrupt number, right? And this is like kind of a mouthful, but when we, look at this in a little bit detail, let me now break down the vector table. And vector table, by the way, is important to understand how the CPU boots up. Once you get this, you will have like no problem reciting how the M-class CPU boots up, right? So this is what happens. At the zeroth memory location of this table, like the first zeroth, not first, but the zeroth offset of this table, whatever number happens to be here is treated as the location where the stack starts, right? That's how it is. The first location, or the fourth address, the entry there, the number there, is pointing to the memory location from where the CPU should start to fetch instructions on a reset, right? And this is related to the boot part, and we'll revisit this in a while. But then starting from this reset vector upwards uh, to the SysTick vector, the numbers are representing how the CPU should handle an exception. So let's say the SysTick or bus fault happens. Let's say bus fault happens, right? You try to, or memory management fault happens, one of those, right? Let's say you floated an address on to fetch some data. That address wasn't available. The interconnect or the bus system responded back with an error. So what should the CPU do? The CPU will take the number that is specified at this offset from the base of the vector table, 14th offset in hex. It will fetch the number available here and jump to that location in memory and start to fetch instructions from there. And the instructions that are available here are a recipe that the CPU can use to deal with this fault, the bus fault, right? Similarly, let's say we program the SysTick, which is a local timer to the CPU. And on the expiry of that timer, when the exception is conveyed, the CPU will pick up the number that is stored on hex 3C offset, right? Offset again from the base of the vector table. So whatever is the number here is the address from where it should fetch that recipe to deal with the SysTick timer interrupt. Similarly, you might have UART, DMA, other peripherals which are mapped onto different interrupt numbers here, right? Let's say interrupt number 31. So when that interrupt happens, it fetches the number from here and goes to that location, fetches the recipe, executes the recipe, and then returns back. Returns back meaning it has attended to the door, metaphorically, returning back is essentially coming back and reading the book. Now, what it does to put a bookmark, so to speak, that's a complicated recipe. We won't discuss it in this series, but know that it happens, right? All right. So now we are talking about how the CPU boots up. So what will happen is when the CPU is powered up, when the software is ready to fire, what will happen is the zeroth entry of the vector table that will be automatically put into the R13 register. Right. And remember, R13 is the stack pointer register. And given that we are starting out, like booting up, the processor will start in thread mode and in privilege mode or privilege state, and it will use the MSP. So this R13 then is pointing to the MSP where this value will be loaded. And that's what, that's what is mentioned here, right? So the zeroth entry then is the MSP. And the next thing that the CPU, and this happens in hardware automatically, what it does is it fetches the number, the address available on the fourth offset and loads that into program counter. And once the program counter has a number within it, it starts to fetch the instructions from the memory location, whatever is stored here. And that is where your initial instructions are. The CPU just back to back fetches instructions and starts to perform the execution of code essentially. So that is it. There are two simple things: load the program counter, load the stack pointer, load the program counter from the zeroth offset and the fourth offset, and just start to execute instructions. That's how an M-class CPU boots up. And hopefully you're convinced about the vector table, how it works and why it's required, and also how the CPU boots. In the next video, let me just show you like a demo on an emulator, and we'll kind of take a look at all of these registers.